show up. If they don't show up, then they don't show up. Okay, so today's class we're going to cover a lot of material. So I'm going to cut the bullshit that I usually give you guys before I lecture and dive right in. Oh, more people are in the waiting room. Okay, so let me share my screen with you. Today's PowerPoint presentation is going to be incredibly short. It's only 2 pages because I'm going to do most of the science on the board. Okay, so I understand that on Monday you learned about Markovnikov and anti-Markovnikov addition, and if that's not confusing enough, you also learned about syn and anti-addition. And today we're going to continue to talk about Markovnikov and anti-Markovnikov additions. So here's an overview for today's lecture. We're going to spend about 10 to 15 minutes recapturing nucleophile and electrophile, as well as Markovnikov and anti-Markovnikov additions. And then we're going to talk about 3 specific reactions. They are oxymercuration reduction, hydroboration oxidation, as well as ozonolysis. They are all a mouthful, but that's okay. Hopefully by the end of the lecture, you will have pretty good understanding of each of them. So I'm going to terminate this PowerPoint presentation and switch to the board. So I will post all my lecture notes on Canvas so that you don't have to stress about not being able to copy down every single word that I write on the board. So I just want you to pay attention if you can and ask me questions whenever you feel like you need more clarification. Okay, so let's talk about nucleophile versus electrophile. So nucleophile, I always denote it with Nu, a pair of electrons, as well as a minus sign to illustrate that it's electron rich and it wants partial positive. So your nucleophile is always going to want to move to something that's partially positive, whereas your electrophile, which I denote with E+, is electron deficient, and it always wants partial negative. So I know we just started learning to draw reaction mechanisms, and we use those curved arrows in illustrating the mechanisms. And the curved arrows always point toward where the electrons want to go. Okay, so enough theory talk. We're going to do some practice problems. So the first one is incredibly simple. That's a reaction that you learned in Gen Chem. I hope everyone can see it. Yes, you can see it. I have NH3, have a lone pair, plus OH3 plus, and it goes to NH4 plus H2O. Now I want to draw the reaction mechanism for this reaction. What do I do? What's the first thing that I have to do in order to draw a mechanism for a reaction? Anyone take a guess? I'm just gonna sit here and until somebody talks.
Maybe like write an intermediate or something.
Right intermediate, that's a very important thing. But the first thing is not right intermediate. You have to identify what?
The electrophile and the nucleophile.
Yeah, exactly. You have to identify who gives electrons and who receives electrons, right? Okay, good. So in this case, who is our nucleophile? That's electron rich and wants to see partial positive.
NH3.
The NH3, why is the NH3? Why not the OH3 plus?
Well, I guess if you look at charges, O is already a positive charge, right? So if you compare a 0 to a positive charge, the NH3 has more electrons to give that lone pair versus that O.
Yeah, that's absolutely correct. So every time you see a lone pair, you have to be very careful because lone pairs are free electrons and they always would love to react, especially those lone pairs on oxygens and nitrogens. So in this case, we have a neutral nitrogen with a lone pair on it. Therefore, where should this lone pair go in order to produce the products that we have, NH4 plus and H2O?
To a hydrogen?
It goes to a hydrogen, and then what? Are we done?
No, the bond from the hydrogen to the oxygen, those electrons go to the oxygen.
That's wonderful. So we take this hydrogen without its electrons. So where do the electrons go? Well, you'd have to dump them somewhere, and oxygen is a perfectly good electron acceptor because it's electronegative. Therefore, we're just going to dump that lone pair onto the oxygen, and we end up with 2 lone pairs on the oxygen. Well, I'm missing a lone pair here. 2 lone pairs on the oxygen, and we have a positive charge on the NH4. Any questions regarding this reactions that we just went over? Okay, no. I'm going to go over an exam problem that you had this past Sunday, I believe. If you have questions about this exam question, you should pay attention to what I'm drawing on the board. So these 2 reactions that I drew on the board are actually very similar in terms of reaction mechanism. Oh, can you guys see? Yeah, you can. Okay, so what's the first thing that I gotta do? Somebody other than Nestor, talk to me.
Identify the nucleophile and electrophile.
Thank you, Anzela. Identify nucleophile and electrophile. What's the nucleophile? Who has more electrons just floating around doing nothing?
Molecule on the left.
The molecule on the left. So this molecule is, if I remember this correctly, it's acetone. So it's a very common chemical solvent that we use to wash our glassware. So acetone, all right? We identify acetone to be our nucleophile. So what's our electrophile?
H3O.
H3O plus. So how do I draw my arrows in this case? I start from this lone pair, whichever lone pair, it doesn't really matter, they're the same.
The lone pair goes to the oxygen, which
It goes to the oxygen, it goes to the hydrogen.
hydrogen.
It goes to the hydrogen because those 2 reactions are mechanistically pretty much the same. So my lone pair is going to go to the H, and are we done?
And then the electrons from the hydrogen go to the oxygen, therefore the oxygen would have 2 lone pairs.
Wonderful. So from this reaction, what I'm going to get is a protonated acetone, which has a plus charge, and H2O. You can see, ish, you know. There you go. Okay, so that's nucleophile and electrophile from me. Any questions regarding these 2 examples that we went over, or any comments? Should I go over more more examples for you to better understand the concept, or we good? I think we're good. Okay. All right, so we're done with reviewing nucleophiles and electrophiles, which are very important for reasons that you will see once we start talking about those complicated reactions. And now we're going to talk a little bit about Markovnikov versus anti-Markovnikov addition, Markovnikov versus anti-M. Just shorthand notations because I'm too lazy to write the full name. So use one picture to illustrate the difference between the 2. I have an asymmetric alkane on the board, and I'm going to add a nucleophile to it. So for Markovnikov addition, where should I draw my nucleophile? Is it on the more substituted carbon or the less substituted carbon?
The more substituted carbon.
The more substituted carbon. Good. So I'm going to draw my nucleophile right here. This is Markovnikov. What about anti-Markovnikov? Where do I draw my nucleophile?
The less substituted carbon.
It should be on the less substituted carbon. So on the other, so that's anti-M.
What do you mean by more substituted?
So good question. So substitution means that you have things other than hydrogen. For example, we have two carbon centers that we're looking at, right?
Yeah.
Alkene. So the carbon on the left, it has two methyl groups, whereas the carbon on the right has one methyl group. Which carbon is more substituted?
The left?
The one on the left, because it has two things that are not hydrogen. Cool?
Okay. Yeah.
Okay, awesome. All right, so anti-Markovnikov versus Markovnikov. I'm gonna give you, just as a summary, a couple of examples of each. So for Markovnikov, as you learned in last lecture, Markovnikov, we have hydrohalogenation, which basically is that we take our simple alkane that is asymmetric and we add some sort of XH. X could be bromine, chlorine, fluorine. Well, fluorine is very uncommon because HF is a nasty chemical to deal with. So mostly hydrobromic acid or hydrochloric acid, which is HCl. And we're going to end up with the bromine on the more substituted side and the H on the less substituted side. So that's one example of Markovnikov addition. A second example would be halohydrin formation. So again, I'm going to take the same simple asymmetric alkene, and I'm going to add Br2 and H2O. So in this example, my OH is going to end up on the more substituted carbon, whereas my Br is going to end up on the less substituted carbon. Any questions regarding the two examples that I believe Sydney and Samantha covered on Monday?
What happens to the extra hydrogen?
The extra hydrogen, you mean in the second example?
Yeah, like in the water.
Like in the water, it just, see here's a Br2 and you got H2O, and OH adds here, one Br adds here. The side product is HBr.
Oh, okay. Okay.
Yeah.
Thank you.
You're welcome. Okay, a third example would be oxymercuration reduction, which is an experiment and reaction that we're going to talk about in this lecture. So I'm just going to skip that for now. And that's two examples for Markovnikov addition. And for anti-Markovnikov addition, we learned very briefly about, what was that? Radical halogenation. So same asymmetric alkene, and I'm going to treat it with HBr plus ROOR. ROOR could be any peroxide. R stands for any alkyl, so we could have methyl methyl, methyl ethyl, doesn't matter, or just hydrogen peroxide. And with this, or with this plus heat or light. So the heat or light is to promote the generation of free radical, which appears as OR dot. So the specific mechanism you don't have to know for the scope of this program. Just know that if you see HBr plus some radical initiator, you will have anti-Markovnikov addition instead of the one that follows the rule. So in this case, if I do an anti-Markovnikov addition, where should my Br end up at? The
The less
carbon,
substituted?
the less substituted carbon, yes. So it's going to end up here. And my H is going to go on to the more substituted carbon that's right there. And a second example would just be another reaction we are going to talk about in details today. That's hydroboration oxidation. It's a mouthful, I understand, and it's okay. It will grow on you, I promise. Okay, so that's all for the recapture that I planned for us. Any questions regarding everything that I just talked about? The board is falling down. Okay, there we go. All right, so two very long reactions that I mentioned just now, oxymercuration reduction and hydroboration oxidation. They're both reactions that transform alkenes to alcohols. Okay, so the first method that I'm going to talk about, you can write down this very long name, oxymercuration hyphen reduction. Well, from this name of the reaction, we can sort of guess, this is a two-step reaction. It's not just simply a concerted step. So I'm going to write down the overall reaction first, and then explain the mechanism for each step. And you can ask me any questions you want. You can interrupt me or whatnot. Okay, so the overall reaction is very long. So I'm going to draw a very generic alkene that is unsymmetric. I'm going to draw R, CH2, and plus mercury acetate, LaC2. And the mercury has a lone pair on it that we have to remember. And plus water. Now the reaction goes, the first step is that we're going to treat it in THF and water. THF is an organic solvent. It stands for tetrahydrofuran. It looks like this. Basically a 5-membered ring with an oxygen on the top. So we carry out the first step in THF and water because we have mercury acetate, which is insoluble in organic solvent, and we have this alkene, which is insoluble in water. So if we mix the two solvents, everybody can dissolve and reaction can happen. The second step is the reduction step, which is sodium borohydride and NaOH. What's going to end up forming is I'm going to redraw my CRR, very generic alkene. And instead of drawing a double bond here, I'm going to draw 2 single bonds with 2 different things attached. I'm going to add an OH to the first carbon and an H to the second carbon. Just by the look of the product, what kind of addition is this? Can anyone take a brave guess?
Sin?
Is it Markovnikov or anti-Markovnikov?
Markovnikov,
It's Markovnikov. Why?
because the OH goes to the most substituted carbon and the H goes to the most to where the most hydrogen is.
Yeah, the hydrogen-rich side gets hydrogen-richer. Therefore, this is Markovnikov addition. Okay, so that seems complicated enough, and I'm going to break it down to you so that we can go through the mechanism step by step. Are we done with copying the reaction overall? Okay, wonderful. So let me go into the first step. step 1 is the oxymercuration step. Step 1. Oxymercuration. I'm just not going to write out the full name. Okay, so I'm going to draw out the generic alkene that I start with, CH2, Cr2. All right, so if you look at your notes, the other important reagent we have here would be mercury acetate. So I'm just going to place my mercury acetate here on the bottom. Now, what's the first thing that we want to do before drawing the reaction mechanism that we just practiced at the beginning of the class?
Which one's the nucleophile and which one's the electrophile?
Yes, which one's the nucleophile, which one's the electrophile. So this one is very tricky. This one, because we have a double bond, which is electron rich, and we also have a metal with a lone pair, which is seemingly electron rich. So which one do you think is the nucleophile? Gonna give you a hint. This is very similar to the addition of Br2 to an alkene.
Aren't lone pairs more unstable than double bonds? So shouldn't we give preference to taking the lone pairs and reacting with them versus breaking the double bond?
You're absolutely right in that the lone pair will absolutely react. However, who's going to go first is an important and interesting question. In this case, we're going to have, how do I say it? A concerted addition. So you're absolutely right in that the lone pair is going to do something so that the double bond gets broken. So my lone pair is going to attack one of the carbons, and the double bond cannot stay the same anymore because that carbon seems very angry right now. It has 5 bonds, so I gotta break that double bond. Where should my double bond go then after I break it? Again, it's very similar to the Br2 addition.
To the oxygen?
It's going to go to very close.
Or the...
It's going to go very close. You're going to form like a triangle.
The mercury?
It's going to, yes, Alex, thank you. It's going to go to the mercury. And are we done? We're not done, right? Something doesn't seem very okay. Mercury now has 4 bonds. You think it's happy? I don't think our mercury looks very happy right now. What are we gonna do to the mercury? Can you take a guess?
Would the 2 bonds like that are connected to the mercury go to the oxygen?
Will the 2 bonds go to the oxygen? You mean
Like,
one of these?
Yeah, like that goes to the oxygen, and then the other one.
Exactly right. That's exactly what's going to happen. You see the mercury is becoming very crowded. It's very not happy. So one of the acetates is going to leave. Therefore, in order to show that the electrons leave with the oxygen, we're just going to draw the arrow so that the arrow points at the oxygen of the acetate. Okay, so what do we get from this step? Try to draw it on your own and look up at the board and see if we have the same answers. I'm going to draw, okay, CR, CH2, G. Do we have similar answers? Yeah, I see a bunch of people nod their heads. That's good. That's good. Okay, cool. So we're here. What's the other reagent that we have not introduced yet in this reaction? If you look at your notes, what's the other thing?
Water.
That's water, right? Where do we even add the water? If you look at the product, can you guess where the water goes?
To the oxygen and the acetate ion.
Water goes where? Sorry.
To the like oxygen acetate ion and the positive charge with the mercury.
The water would go, you mean here?
No, I meant.
Or here,
No,
up to this carbon?
No, I meant to the ion. That's.
Oh, I see. You mean that the water is going to go to this ion?
Yes.
I see. Okay, so it is very possible that they're going to form an association due to the fact that there's a negative charge and oxygen loves negative charge. However, is that going to give us our product?
Oh, no.
Probably not, right? It's not a productive association. So you're right in that it's possible they're going to associate, but that's not going to give us our product. So in order to move forward, where do you think the water has to go? If you look at the structure of the product, right, we have an OH somewhere in this molecule. So I would assume that the OH comes from the water. So which carbon should I go to?
To the one with the R groups.
Yes, to the one with the R groups. That's excellent. Am I done? Is this carbon happy now? Some of your heads. Okay, Anthony, why is this carbon not happy?
Because it has 5 bonds now.
And it has 5 bonds. So what are you gonna do?
Do you remove the bond from the carbon and the Hg?
Absolutely. We break this carbon-mercury bond. And now what do we have? Our carbon is happy, and our mercury is going to be very happy because it's now neutral. You give it back its lone pair on top, and it only has 2 bonds. So we have this kind of happy-ish molecule that looks like this. Try to draw it on your own, and we can compare our answers. Mercury.
So what was our neutrophil, like electrophile?
I'm sorry?
What was the electrophile and neutrophile from the beginning?
What was the electrophile nucleophile? That's a very good question. So let's think about this. So we drew the arrows in this way. We drew that the oxygen lone pairs attack the carbon. So there's a term called nucleophilic attack. Don't know if you've been exposed to that term yet. So nucleophilic attack means that a nucleophile attacks an electrophile. So wherever your arrows are going from, that is your nucleophile. So in this case, which one's the nucleophile?
The carbon with the R.
Why don't you take another guess?
The water.
Remember, the nucleophile is the one that has more electron density. So between the water with 2 lone pairs and the carbon that has no lone pair, which one has more electron density?
The water.
The water, right? Therefore, the water has to be nucleophile or electrophile.
Oh, okay.
The water has to be nucleophile, right?
But we didn't start with water. And we have the 2 molecules that we started with. There was no water there.
What? Sorry, there's no
water in the 2 molecules that we started with.
We started with 2 molecules, and water and THF are the mixture of solvent.
Oh,
So we have a huge amount of water and a huge amount of THF.
okay.
Good?
So if the water is the neutrophile, what's the electrophile?
Water is a nucleophile.
Right. Which one is the electrophile?
Which one's electrophile? That's a good question. Who are you attacking?
The carbon?
The carbon, therefore, who's the electrophile?
The carbon.
The carbon. Whoever you're attacking, whoever's receiving your electrons is the electrophile.
Okay. Thank you.
Okay, cool. So we're at this step. Do we look very similar to the product now, at least somewhat? Ish, right? So two things we have to change in order to go to the product. First of all, we got this mercury thing hanging out. Secondly, we have this water thing with the positive charge hanging out. So I'm going to take care of the water thing first because it looks like an eyesore. I want my OH. I don't want this H2O with a positive charge on it. So let's not forget that we have this acetate ion floating around from our previous step. What do you think the acetate ion can do to this water with a positive charge?
It will attack it.
It will attack it. How?
The acetate ion attacks the hydrogen, and then that goes, the electrons between that bond goes to the oxygen.
Wonderful. That's exactly what happens. So what we're going to end up with, again, try to draw yourself to C, and then look up, compare our answers, see if we have the same thing. Got the same thing? Okay. I can't see most of your faces, but for those of whose faces I could see, you're all nodding, so that's a good sign. All right, so we took care of half of the product. Now we're done with the step one, which is oxymercuration. Let's not forget that there's a second step, which is reduction. So because we have this mercury hanging out here, and the second step is reduction, it must be that the reduction takes care of the mercury and turns it into an H. Okay, so let's work on the second step. So you don't have to know the mechanism for the second step. I'm just going to draw it out for you. And all you need to know is that it changes the mercury to an H. All right, so we have Cr2, CH2, OH, mercury acetate. And I'm going to react that with sodium borohydride as well as NaOH. In the end, I'm going to get generic Cr2, CH2, H, and OH. And the H comes from the sodium borohydride, which is the hydride source, which gives you H minus instead of H plus. And we have our side products. Let's not forget. What are our side products? We have sodium BOH4. We have 4 mercuries precipitating out. And we also have 4 acetates that are just chilling. And the most important thing is that we went from an alkene to an alcohol. And all the side products, you just have to know them, but during an exam, you don't have to write them all out. They're not that significant. Okay, so any questions regarding this reaction that we just talked about? it took us 20 minutes to go through this one reaction. I want to make sure that everybody understands what happens. No questions? Yes.
This part over here that you went from the Hg to the hydrogen, like I don't understand how that just happened. Like,
Right, you don't have to worry about the mechanism. It's okay. So for you, what you have to know is that for the mechanism of the first step, you form this very important intermediate, but for the second step, you don't need to know the mechanism for.
Okay.
Yeah, just know that the mercury gets replaced by the H. That's sufficient for the scope of this course. Any more questions regarding this reaction? If not, we're going to move on to the next one, which is going to be easier than this one. Okay. If you know how to do this one, the next reaction is not going to be that difficult at all. So the second reaction that we're going to talk about in details is hydroboration oxidation. Hydroboration. So the overall reaction is much shorter. Cr2, CH2, step 1, we have boron and THF. Step 2, I have hydrogen peroxide as well as NaOH. And the end product, then R2, CH2, is this. So based on the look of the final product, is it Markovnikov or anti-Markovnikov?
Anti?
It's going to be anti-Markovnikov, right? Because the hydrogen ends up on the more substituted side, whereas the OH ends up on the less substituted side. So how does this even work? Well, we have 2 steps. So as we did before, I'm going to break it down and show you the most important mechanism, which is the 4th step. The 2nd step, you don't have to worry about it. So I have my alkene, and the other reagent that we're paying attention to is HB3, HB3. Doesn't matter. I just want you guys to focus on one BH bond right now. So what's going to happen? Well, this is what's going to happen. I'm going to draw a transition state. A transition state is different from an intermediate in that a transition state is not isolable, whereas an intermediate can be isolated and it actually exists. A transition state is more like a model that people predict what would happen. So experimentally, we determined that this reaction happens this way. BH2, and we have R2C, CH2. And this is what happens. So boron is a very interesting element. It makes only 3 bonds, but it's never happy. When it has 3 bonds, it's boron neutral, but it's electron deficient. It only has 6 electrons. So it violates the octet rule. And what happens when something violates the octet rule? Like it has less than 8 electrons. Does it want more electrons or does it want to give away electrons?
It becomes an electrophile, so it wants more electrons.
It wants more electrons, right? So that's exactly what happens in this case. Your BH3 starts with 6 electrons and it's very not happy. It wants more electrons. Therefore, well, you give it an alkene. That's a lot of electrons. The alkene double bond is going to break and 1 pair of electrons is going to go into the boron. But boron is a very temperamental guy. He's not very happy with 4 bonds either. He doesn't like to have extra electrons, even though he's now satisfied with the octet rule. So instead of holding those 4 bonds, the boron's going to break the single bond with H and dump that pair of electrons onto the carbon on the left. So this transition state is possible just because boron is a very temperamental guy. Doesn't like to be 3 electrons. It doesn't like to form 3 bonds because it's electron poor. Doesn't like to sustain 4 bonds because it's too electron rich. So what are we going to get from this? Well, we're going to get this R2C, CH2, and we have BH2. And to this, we add an H, right? We break this BH bond and we move this H onto the carbon on the left. That's what we have. So just now we focused on one BH bond and this process happened. This is not the only time that this process happens. We have 2 more BH bonds, therefore this process can happen 2 more times. So imagine in your head that you're going to replace those 2 H's with this bunch of stuff 2 more times. So what we're going to end up having is this boron with CH2, Cr2, and an H. And we have 3 of those things attached to the boron. Any questions so far? Because this is the mechanism for the first step, which is the more important step.
What does the 2x represent?
The 2 R's?
It says 2 times.
2 times, yes. So the same process happens twice. We good to move on? Emanuela, are you saying something? Sorry.
Yeah, I'm saying, can you hear me?
I can't hear you very clearly. Okay, you can probably stay after the class. We can have more discussions about this. Okay, so that was step 1. Do we look close to our final product at this point? Probably not, right? Probably not very close. We have the basic structure, but we're missing an entire OH. All right, so that's what the second part takes care of. That's what the oxidation comes into play. So keep in mind the final structure looks like this. And then we're going to treat it with something else. It's boron. I'm going to redraw the structure, CH2, Cr2H. Repeat 3 times. And I'm going to treat it with 3H2O2. 3 equivalents because I have 3 of those things attached to my boron center. And also I'm going to throw it in a sea of NaOH, so excess. What I'm going to end up getting is that I'm going to replace my boron with my OH. I'm going to replace my boron with OH 3 times. Therefore, what I'm going to end up generating is going to be 3 OH, CH2, Cr2H. That's it. Plus a bunch of side product, which we don't care about. And like I said, the mechanism for the first step is not important, so you don't have to stress over how to replace our boron with OH. Just know that in the end, we do the second step to do the oxidation so that the boron comes off. And you generate the alcohol product, which is what we want. Any questions regarding the second step? No? Okay, good. Yes.
Does the excess NaOH, so the OH is what's required for this step, right?
Yes.
What happens to the Na? Does it react with anything or does it just sit there? Like
what happens to Sorry?
The Na plus ions from the NaOH, do they react with anything or do they just sit there?
That's a very good question. It is a spectator ion. So here we have a negative charge, right? Your Na just sits there to balance out the charge. Didn't write it because I was lazy. Anyway, so let me just give you guys a very quick overview of these two reactions. So we learned two ways of generating alcohols from alkenes. One of them, I'm going to go R2C, CH2. So we learned two ways. One of them is going to give us Markovnikov product, which is R2C, CH2, OH. And that is oxymercuration reduction. Whereas the other method is going to give us anti-Markovnikov product. That is hydroboration oxidation. And which method to use is entirely up to the question that's asked. So I ask that you pay extra attention to the regiochemistry of the final product that's required of you in your exams and homeworks. Both reactions are very nasty, and we no longer practice them in chemistry nowadays. I believe, especially with mercury alkyl bonds, that's the most toxic type of mercury alkyl bonds. And I remember it was probably Emory University, there was a professor who wore the wrong type of gloves when she conducted experiments with some sort of alkyl mercury reagent, and she died a couple of days after doing that reaction, just because she used the wrong pair of gloves. So very nasty stuff. We're now learning very old school chemistry invented by very old white dudes. Just keep in mind that they're no longer being used. You're learning this just because, you know, for historical reasons. And also the mechanisms are really cool. All right. Drop my pen. The one last reaction that I'm going to talk about is not going to involve you memorizing reaction mechanisms. So if you take one thing away from this class today, I want you to remember this last reaction. That is ozonolysis. So there are two types of conditions under which you can carry out ozonolysis. Condition number one. I'm going to draw my simple generic alkene again, CH2. Treat it with O3, which is ozone, and then treat it with dimethyl sulfide, CH3, 2S. What I'm going to end up generating is, basically, look at this alkene. I'm going to cut it right in the middle, and I'm going to make R2C, give it an oxygen, plus CH2 with an oxygen. That's a pretty neat reaction. You split the molecule and make two new ones out of that. So from this reaction, you get a ketone and another ketone. Oh no, it is actually an aldehyde. So this is reaction condition one, where you treat it with where you treat it with dimethyl sulfur. Okay, so condition number two, I'm just going to erase the parts that are different.
What happens to the oxygen number 3?
Oxygen number 3?
Yeah, is it just floating around freely?
I believe it's going to form this thing called DMSO, dimethyl sulfoxide.
Okay.
That's the side product.
Okay.
Okay, so good question. And the second condition, second set of conditions that you can carry this reaction out under. First, you treat it with O3, same thing happens, and then you just throw in a bunch of water and hydrogen peroxide. What's going to end up happening is that you're going to cleave the molecule the same way, make the same ketone, And instead of an aldehyde, you're going to end up generating a carboxylic acid. And that process is called hydrolysis, which you will learn in second semester Orgo, so don't worry about that yet. Just know that ozonolysis is a very neat reaction from which you can generate 2 carbonyl compounds at one go. Okay, so any questions so far regarding anything I've talked about? I'm done lecturing. Now we have about 10 minutes left, so that's question time. If you no longer have any questions, you can feel free to leave. For people who want to have more discussions, you're more than welcome to stay.